Let's start today for a new topic, power cycles. This topic will study for all types of power cycles. What we're going to study today, we'll study the ideal cycle first, the concept of ideal cycle related for Carnot cycle. Then going to a practice one, like we study Rankine, we study Brighton, we study some basics and simple information about other cycles like Otto, diesel, and Dole. Also, we study some data about four-jet engine. And we convert to another topic of the cycle, which is reversed cycles. And we start also by ideal one, reversed Carnot cycle, and we're going to the practice one, which is represent for refrigeration or vapor refrigeration cycle, For the basic of Carnot cycle, first, Carnot cycle, it's a have four process. Some basics, it can be used for all coming cycles. These basics like, first, almost all cycles have a four process, 1, 2, 3, 4. This is closed one, closed cycle, closed processes, closed state from state to state to going to the first state, this said cycle. So here we have a four process. This four process, normally for almost all types of cycle we're going to study today is working between two pressure line, high pressure line and low pressure line. What we're going to see during the session between the cycle and the other, what is the referring for the high pressure line and what is the referred to the low pressure line. Also for calculation of any equipment required, like work required, like heat required, like heat rejected, like work consumption, all this equipment calculation related for the energy, like work or heat, it can be calculated according to the concept of difference between two enthalpies. You know the enthalpy for the first state, the second state for the process. So to calculate if this represent for heat, represent for the work, whatever, if you need to calculate if this work or this heat is equal to difference between the two energies of this point, difference between two enthalpies of this point. So it should be aware for the enthalpy for first point, aware for the enthalpy for the second point, okay? For special cases like the cycles, which is a media for air, this is like under umbrella for ideal cycles. Ideal gas. The media here is ideal gas. So for the ideal gas here, ideal gas cycles, this is we can represent for the enthalpy with temperature. As per Joule's law, the enthalpy is a function for temperature only. This is the normal sequence we know. Okay. This basic is important. Why? Because this gives you like a strategy for any problem coming to understand, to solve any question easily without any saving and memorizing a lot of information. Not the same information what we talk about for the power cycle, Rankine cycle. This is the same for Brighton cycle as a concept. Maybe inside details it is different, but the concept at least it is the same. So this is going to reduce the amount of knowledge or amount of saving information, not knowledge, information in your mind. Okay, fine. Carnot cycle first. This is Carnot cycle. Here is ideal cycle. The four process here is two process isothermal, two process isentropic, two process isothermal, two process isentropic. What is the two process isothermal? This process 1 to 2, and this process 3 to 4. This is two process isothermal. This is the process isothermal for the heat. For example, from 1 to 2, state 1 to state 2. This is for heat input. This is isothermal process. And from 3 to 4, this is for heat output. This is also isothermal process. So we can conclude for the two process of the heat, whatever heat in or heat out, this is isothermal process. What's the meaning of isothermal? As per discussion for thermodynamic, the temperature constant, temperature constant. So what is the second process? 2 to 3 and 1 to 4 or 4 to 1. These two process, it is isotropic. But here, once ask me, no, it's adiabatic. No, it is not only adiabatic, this is adiabatic plus reversible. This is adiabatic plus reversible. Adiabatic plus reversible. So if adiabatic plus reversible, this is, we can conclude this, his name is isentropic. What is the meaning of isentropic? No change of entropy. No change of entropy. Delta S is equal to 0. No change in entropy. So here, as we discuss again, this is 2 isothermal process, and this is 2 isentropic process. Okay, fine. So from 1 to 2, this is reversible isothermal expansion, and 2 to 3, this is isentropic expansion. 3 to 4, reversible isothermal compression. 4 to 1, this is isothermal compression. This is for the idea of the cycle. What is also important, actually, this is the important point here for this cycle. What is it? Efficiency equation. What is efficiency equation equal? It is equal to, this equation is equal to T hot minus T cold divided by T hot. Again, efficiency is equal the difference between the two temperatures, T hot and T cold, divided by T hot. This is very important equation. Okay. In a Carnot cycle, heat is transferred at
constant temperature.
Carnot cycle, heat is transferred at constant temperature. Same process. Which of the following statement is incorrect? Which of the following statement is incorrect?
A.
Or reversible cycle has the same efficiency. Actually, Carnot cycle, it is the maximum efficiency for all cycles. But maximum, not all Carnot cycle is the same efficiency. All is maximum, but this is maximum related to the not ideal one with the same condition. So it is maximum for this condition, for the temperature hot and the cold, for this condition. If we change the two temperature, the efficiency is changing, but we obtain a maximum for this case. So all the time it is maximum, but according to the condition of the temperature. Carnot cycle operates between 400 Fahrenheit and 250 Fahrenheit. The maximum theoretical efficiency of the cycle is most nearly efficiency equal T hot minus T cold divided by T hot. So 400, 250 divided by 400. What is the answer, please?
0.6. 0.38.
Answer, please.
C.
As a regular answer, it will be obtained 0.38 as per these conditions like this. But this is not correct. Why? Because we have a problem for what? Yes, as you see. For temperature. Temperature, it must be absolute. What's the meaning of absolute? Kelvin or Rankine? One of this. This is Fahrenheit. So, as you wish, you can change it to Rankine, or you can change it by Kelvin in the calculator, conversion calculator. For the numerator, if you follow Rankine, if you convert to Rankine, no problem for the numerator. You can keep it as it is, because delta Fahrenheit is the same delta Rankine. And all you need to change this. So the correct of this, it will be 400, 250 divided 400 plus 460. You got it, your answer, 0.17. Someone, no, I don't remember to convert it from Fahrenheit Rankine because not in the conversion calculator, I need it to be Kelvin. If you follow Kelvin, should be all temperature changed. This is change, this is change, this is change according to Kelvin. Why? Because delta Fahrenheit not the same delta Kelvin. So if you want to follow Kelvin, change all temperature Fahrenheit to Kelvin and continue equations by all numbers Kelvin and get it the same answer. Okay? Heat engine classified into main categories. This is now we are going to the practice one. We finished the ideal one. So the practice one here classified into categories, external and internal combustion engine. For external combustion engine, we study here steam power plant. And for internal combustion engine, we study two types, rotary and reciprocating. The rotary will study gas turbine, which is a cycle here is Brayton cycle. And for steam power plant, we study Rankine cycle. And for reciprocating, we'll study Petrol cycle, which is petrol spark ignition engine. This is Otto. And diesel compression ignition engine. This is diesel. And we study one some in between Otto and diesel. The yellow here is what we're going to study. But for the part of reciprocating, just we're going to one slide for the basic information for this part for reciprocating. What's going for the main calculations and the numerical part? This is for rotary, which is Brayton cycle and Rankine cycle. And what is coming in the exam a lot? Brayton cycle number 1, second is Rankine cycle. Second point, normally not all the cycle is coming in the exam, just as the part of this cycle is coming. Not at all is coming, just a part is coming. Okay? The screen is okay, it's fine for all. Screen is fine for all. Rankine cycle, what is the 4 element here? Boiler, turbine, condenser, pump. This is the 4 element. Boiler, this is the source of heat added. Turbine, this is the source of electrical, turbine work. Condenser, this is the heat rejected. Pump, it is the consumption power. The media here is water of the part. The second part is steam, which is a type of the water also, but in another phase. Okay, so the media here is water and steam. The water profile here is presented by by this curve. You see this curve? This is the curve for the steam, water steam is presented as this, something like this. This is represented for water steam. And the constant pressure line is represented as it is. This is the constant pressure line. This is the presented pressure line. So this, for example, it's like B at B1. Constant pressure line. Okay. Why is this constant pressure line follow like this? Here in the subcooled area, this is subcooled area. This is superheated area. What is inside here? This is the media mix. This is for liquid, for the steam, this is mix. So for adding heat, the start of the fluid is going to raising in temperature because the temperature increase like this here. This is the scale of temperature. Up to reach to the saturated liquid line, which is starting for boiling, starting for steam, this point. So here at this point, any heat added, not for increased temperature, only for change phase. So during this pass, such a change phase from fully liquid to fully steam. Once it's fully steam, any energy or heat added more is going to increase here in this area to increase temperature again without any change of phase. This is said superheated steam. This is what we'll see here. As we discuss, 4 element, we discussed already. What else? Working between 2 pressure line. This is the first one. Just change line on this. This is the first one here. This is the second one here. The low pressure line and the high pressure line. One moment, please. So this is the two lines here, one for the boiler, one for the condenser. So the pressure, the high pressure line, it is for boiler. The low pressure line, it is for condenser. Again, for high pressure line, it is for boiler. The low pressure line, it is for condenser. Okay, fine. So this is the pressure line high. This is the pressure line low. This is the range of the, where this is the range of high pressure line. This is the range of low pressure line. Great, that's fine. We started by point 1 here into the pump. So this is the point into the pump. At least saturated liquid. It's better to be subcooled to be sure this is fully liquid. This is pump. So we need to be sure this is pure water. So from this going up, isentropic process. So the pump process is isentropic. Also turbine, pump and the turbine is isentropic process. Normal the parts for the work calculation, it is isentropic. The part for the heat added or heat rejected, normal it's happening during constant temperature. So by the way, this is point 1 to point 2. This is isentropic process for the pump. Then from point 2, this is heat addition. So it's going along the constant pressure line here. You see, constant pressure line for the boiler. Up to 3. 3, this is the output of the boiler going to the turbine. This is in superheated area. It's better for sure. Here is not better. We prefer to be, it is in more superheated. This is better to give us more energy. Then going to expansion here for the turbine to obtain the work from 3 to 4. For 3 to 4, this is also isentropic process. From 4 to 1, this is condenser pressure. Condenser process here from 4 to 1. So we can conclude this what we discussed here for the cycle. Pump, it is isentropic. We can calculate the work of the pump difference between two enthalpies. It's a concept. Don't save a lot. It's a concept. Difference between two enthalpies. So the pump here between what? 1 and 2. So H2 minus H1 or H1 minus H2. This is the pump. Okay, that's fine. While we write two equations for any calculation for the pump, for the heat, for the work, for anything, we can represent by two equations, heat or work. We can represent it by two equations. The first equation, if it is included mass flow rate, in this case, the unit here is unit of power, or without m dot, without heat transfer, like this, H1 minus H2 only. This is said specific, like if it is work, specific work, kilojoule per kilogram. If it is heat, specific heat, kilojoule per kilogram. This is being specific per kilogram. But if you multiply for mass flow rate, it is now is kilowatt. Normally, we don't found m dot, so normally calculate specific. If it is in case given m dot, we can follow m dot in the equation. Boiler from where to where? From 2 to 3. This is boiler for heat addition. So at constant temperature line, so m dot H3 minus H2 for H3 minus H2 direct. For turbine from 3 to 4, so H3 minus H4. That's it. Yes, that's it. Fine. Isentropic process. From 4 to 1, this is condenser pressure, constant temperature for the condenser from 4 to 1. Yes, exactly. How to calculate is this heat rejected H4 minus H1. That's it. Yes, that's it. So the concepts I give to you at the beginning to just reduce the energy required to memorize everything and everything. That's fine. Efficiency as a general definition, output by input. What is output here? Output is work turbine, but we take some of this work in to operate the pump. So the work turbine minus work pump, which is this is mean work in it. Normally for the Rankine cycle like this, the work of pump, it is compared to the work turbine, it is very small. So we can neglect work pump. So sometimes we consider only work turbine and go to proceed for the calculation with this work turbine. If it's given work pump, so calculate it, no problem. Add it and calculate it, consider it. Divided by the source of the heat. This is the input. So divided by Q boiler. Can we improve the efficiency and so on? Yes, we can improve the efficiency. We can improve the obtaining power and so on. How to improve that? By two ways. Then for the numerator, it is the work turbine. So increase the work turbine. For the denominator, it is the Q added. So decrease the Q added. Both cases is going to improve our efficiency. By the way, we have three options here to increase efficiency. What is these three options? According to the cycle, if we just play and study the effect of the pressure lines, for example, we have two pressure lines. One condenser pressure, it is a low one, and one boiler pressure, it is a high one. So if we decrease more the condenser one or increase more for the boiler one, what happened? The range between the two lines is increased. So the expansion of turbine increase and so on. This is what we'll see. The condenser pressure. If condenser pressure decreases like this, decrease from here to there, what happens? Expansion of turbine increase. So we obtain more efficiency. But we have another problem. This is distance. This is distance from the point up to the saturated vapor line. Yes, check here between this point and saturated vapor line is going to be far. What does this represent? This is represented the amount of steam in this mixture between steam and water. So this is represented the amount of steam, which is said dryness fraction. Said what? Dryness fraction. So here represent X is this, X, this is dryness fraction. Dryness fraction. So we'll find the dryness fraction here for this point, maybe around 0.9. So for this case, it is around 0.8, something like this, 0.82, whatever. All in all, it is less. So the dryness fraction is decreased. The dryness fraction is decreased. Second case, we can study effect of boiler pressure. If you increase more boiler pressure, this is increased here for boiler pressure. This case, this original, I increase more at the same temperature final. What happened? Also on the same concept, the work increased. The work what? Increased. And the dryness fraction also have a problem. Dryness fraction is back, which is decreased. The third option for this is increased temperature. What's meaning of increased temperature? This is the temperature, for example, for first state. For second state, going to be up like here in superheated area. What happened during expansion? This is going to expand. This is the previous, which is It's clear the range of expansion for the case of temperature increase is higher. So this option is increase efficiency also. What about for dryness fraction? No, this is the only case for dryness fraction increase also. Dryness fraction is increase also here. From this point, upgraded to this point. So we can take a conclusion for this steps. What is this conclusion? This conclusion said, this is final conclusion here. What is said this final conclusion? We can increase the efficiency. We can increase the efficiency by 3 ways. By what? By increasing boiler pressure, by increasing superheating, by decreasing of condenser pressure. So this is the 3 options we have. Okay, how to make this in a practice cycle? Actually,